All right, so this is going to be a whirlwind review of mostly stuff from first semester on vectors, with a little bit of conceptual calculus review. So I'm going to go fast because, again, you should have seen all this already, but this might serve as a nice reminder, or I might explain it in a slightly different way. And I'll probably explain some things at a slightly higher level of sophistication that can help us kind of build from what we already know. So as you take notes, again, think about if you were asked about this, can I do problems related to some of the content that is on this little review whirlwind video. So, vectors. Vectors are something that have both a length and a direction, or a magnitude and a direction. So they are specified by an arrow. So a vector A, has both a length. I could put a ruler down and measure the length of this arrow, and it has a particular direction, which is different from, say, this vector B, which has a different length and a different direction. And this is a definition that is independent of any coordinate system. So this vector here, B, and this vector here, B, which is I just made a copy of these, are identical. I don't need axes to define vectors. These are just something that have some sort of direction and some sort of length. Often, particularly in physics, we usually do throw down a coordinate system, but we will do that in a little bit. First, let's just define vectors in the most general sense. How you operate on vectors and how you play with vectors involve a couple of operations. The first one is scalar multiplication, where I can multiply a vector by a scalar. Again, a scalar being something that only has a length or a magnitude, if you want to think of it that way, and has no direction, where the vector, of course, has both. So if I have a vector b and I want to specify 1/2 b, then that is a vector that is going to be parallel but is 1/2 as long. So in this case, it's not quite to scale, but imagine cutting this in half. That is then this vector here. So it points in the same direction, but has a magnitude that is altered by whatever this coefficient is. In a similar way, then you can define the negative of a vector as thinking of it as just multiplying by -1. In that case, it switches direction. So in this case, negative b is the same length as b, but points in the opposite direction, or is anti-parallel to b. Addition of vectors is by the common parallelogram rule, where if I have vector A and vector B, again, since these are independent of any coordinate system, this vector and this vector are the same thing, I can pick up one of these vectors and move it over and put it from kind of base to tip, and consider that as a way of adding two vectors together. So in this case, if I have a vector A and I have a vector B, I put the base of B at the tip of A, and then I can think of it going from A to B, and then that defines their sum C of A plus B. Similarly, I could do B plus A, and you can notice here that it traces out a parallelogram, and then C goes from diagonal to diagonal, or across the diagonal. So that's the parallelogram rule with adding vectors. And then similarly, since I can think of as the negative of a vector as just being multiplied by a scalar of -1, subtraction can be defined similar. If I want to think of A minus B, that's the same thing as A plus -b. So in this case here, if I want to do A minus B, I can have A, which again I can just copy, and then instead of drawing B, which is going in this direction, -b then goes in that direction, and my parallelogram traces it out in this direction here. In this case, the parallelogram would be something like this. And then D is A minus B. Then, of course, subtraction does not commute. So that is not the same thing as B minus A, because again, then I could go B, and instead of going A, which would go out here, -A goes down here. So I have B minus A as a result. And then these are, of course, then going to be anti-parallel to one another. They're the same length, but opposite direction. All right. So again, we can now put some symbols down to these words. So I'm going to call the magnitude of A, right, the length of the vector A, I'm going to use the absolute value signs across the vector, or I might just draw the letter without the arrow. So we call this the magnitude of A, right? The length. That is just a number, a scalar. It's not a vector. And then I can have this chevron over the A instead of the arrow, and that's going to specify the direction of A. So this vector here is just a direction, and we define that as being a vector with unit length, or we call it a unit vector. So this is just a vector that's magnitude is unity. So in that sense, it's giving us just the directionality. It's not giving us the length of the vector, but then the magnitude is giving us the length. So there, we can then think about it. If the vector A has a length that's given by the magnitude, then I can always multiply it by some scalar. So I can imagine I can multiply it by the scalar of 1 over the magnitude. Right? That's just a number. If A has length equal to the magnitude, then this should have a length equal to 1, because I'm essentially canceling out the magnitudes. So then this can serve as a definition of the unit vector, because I know this is going to be parallel to the original vector A, but I've now made it so that it has length 1. Therefore, we could define the unit vector in the following manner. The unit vector A is 1 over the magnitude multiplied by the original vector. This is usually what's shown, right, as the definition of the unit vector. I kind of like writing it instead as if I multiply both sides by the magnitude, so this goes over here, then I can write down that the original vector is a magnitude multiplied by this unit vector. And notice how I called, this magnitude, and then I called this thing the direction. So in this case, I think this is really nice because it captures that a vector is both a length and a direction. Essentially, you can always write a vector like this, where it is some magnitude multiplied by some unit vector, and then that really is isolating for you that there is a length and a direction associated with the vector. All right, then usually what we do is we impose some sort of coordinate system, and this is, again, to be a little fancier. We're going to always use an orthogonal coordinate system. The Cartesian axes are one such example. The axes are perpendicular to one another. And then if there's a z component, it's kind of out of the page. It's perpendicular to both of them. We will always use an orthogonal or perpendicular coordinate system for reasons I'll let upper level mechanics explain. But in this case then, you can imagine if I have some vector A, and I've drawn it relative to some axes, some coordinate system. And again, this vector does not have to necessarily start at the origin, like I've drawn it. Then this vector has some length and some direction. But then I can also think of it as having some length parallel to this axis. That's this component right here. Then it also has some component parallel to this axis, which is this component here. So I can imagine, by the addition rule, that if I have this vector that starts here and ends here, that's the same thing as if I start here and go down and then go over, along each of the axes. So by the addition rule, I can think of this original vector as having some component in the x direction and then some component in the y direction, where this component is the part that is parallel or anti-parallel to this axis, and then this is the component that is parallel or anti-parallel to this axis. So that's what's called a coordinate decomposition. And therefore, this gives us kind of multiple ways to write a vector, where this is specifying kind of the length along each axis. And so I'm sure you saw all of these last semester, where I could write this vector A as kind of this x component times x hat, where this is kind of specifying this axis, and then the y component times y hat, which is specifying this axis. Particularly notice it's specifying the positive direction of those axes, right? This is where the positive direction goes. This is where the positive direction goes. And then an origin then specifies what is 0, 0. So this is kind of one way to do it. I kind of like the coordinates, using brackets. I know Kittner likes using column vectors. So these are all saying the same thing. And then the engineering notation, writes it, rather than using unique symbols like X, Y, and Z, it just says EI, where it'd be E1 plus E2, E1, E2, E3 for X, Y, and Z. The only thing to remember is that for these sorts of decompositions or these sorts of ways of writing it, right, the context then must be clear of what it's talking about, right? When I write that this coordinate, if in this context, this is the X coordinate, this is the Y coordinate. If I could have different axes. Let me draw an example here. Like the kind of XY that you're kind of used to, kind of in this direction. But there's no reason why I couldn't have axes that, look, say, like this. I'll call it maybe alpha and beta. And then I could write, say, the vector as, some component in the alpha direction plus some component in the beta direction. And then if I write it like this, all right, that's perfectly valid as long as I know that when I write it like this, that these axes are what I'm referring to. Again, we'll always use kind of horizontal and vertical Cartesian, but kind of example where you've seen this probably last semester is like an inclined plane. Like when you had a box on an inclined plane, what you were doing is you would have an axis kind of along this direction and an axis along this direction when you solve Newton's laws of motion, which is different than, say, this and this. All right, so how do we actually get these decompositions? How do we get these components? If we go back up to the original picture, this is the vector, and the vector has a component that is parallel to X and parallel to Y. And just to make it clear, I'm going to just say parallel, but it of course can be anti-parallel as well. So in this case, right, it's parallel to X and technically anti-parallel to Y because it's going down versus up. But when I say parallel, I mean parallel or anti-parallel. So when I think of this vector here has a component that is along the X direction. I can think of that as a projection. If I were to project this vector onto the x-axis, think of it as in I have a giant light bulb, up here. That as it shines down, this vector casts a shadow. That would be this vector would cast a shadow that would be essentially the projection of that arrow along this axis. And if I had a light bulb here shining out, this vector would cast a shadow that would be the projection of that arrow along the y-axis. So to pluck out and extract these components, really what we want to do is think of it as we want to project the original vector onto each of the axes in order to get out these two components. So what we need is a way of taking the original vector and doing this projection. And we do have one of those. We do have an operation that does that, and it's called the dot product. So the dot product, again, I always like to think geometrically, because I can write down kind of mathematical formulas for what a dot product is or whatnot, but we shouldn't allow ourselves to just do math for the sake of math. What we're doing here is we want to think geometrically about what's going on. This dot product has physical geometrical meaning, and I like to, in this case, like it's connected to plucking out these parallel components or thinking of it as a projection. So that's how I'm going to define the dot product. So this is probably different than what you did last semester. So I'm going to define the dot product as the following. If I take some vector A and I dot it with b hat, so I'm going to define this as the dot product, where whatever this is going to be equal to the component of A that is parallel to the b direction. So essentially this operation plucks out the component of A that is parallel or anti-parallel to this direction. So let me draw this with a picture. Let me throw down the axes, and let me have some vector A and then some other vector B. So I'm going to use this to define the b hat direction. And I'm going to ask myself, given this vector, what part of this vector is parallel or anti-parallel to b hat? Well, then that's just this component right here. Again, think of it as a shadow, right? I have my light bulb that's casting a shadow down and projecting it down onto this b hat direction. You think of it as the axis that would be drawn by that vector. So this part here is the part of A that is parallel to b hat. This part then is the part that is perpendicular to b hat. There's another operation that is good at plucking out these perpendicular components called the cross product, which we will see later in the semester. But in order to get this component here, this parallel component, your kind of physics engineering mind should start celebrating, because you should see that, aha, a triangle, a right triangle in particular. So if I imagine this triangle here, let me redraw it down here. All I've drawn here is that I have one side that is the length of the vector A, in this case the hypotenuse, and then there's this component here that is going to be parallel to B, and then this component here that is perpendicular to B. Well, I could throw all the vector stuff away, it doesn't matter, right? Because all I see is a right triangle with some angle theta there. So given this definition of theta, and given that this is the hypotenuse, SOHCAHTOA my way, this therefore has a length of equal to A times the cosine of theta. So, since this was the parallel component of A, which we are saying is the dot product here, therefore is just A times cosine of theta. And again, the SOHCAHTOA stuff, again, hopefully that's, you remember all this stuff. But again, which is cosine, which is sine? I always like to think, if you know the hypotenuse, and I have the swoosh, theta, when I'm defining my angle, the swoosh touches the cosine part, and then the opposite side is the sine, right? So the adjacent is what the swoosh touches, and then the opposite side is not being touched by the swoosh. I think I just like saying swoosh. All right, so anyway, the component of A that is parallel, we just said here, is the magnitude times cosine theta. Now that might start to look familiar, because I can then multiply everything here by the magnitude of B. So that's where I'm going to do that here. So I have the magnitude of B multiplied by this dot product. And I'm going to take, really I should be proving, distribution and all this stuff, but we'll let the math majors think about that. So I have this magnitude of B multiplied by this dot product. I'm going to move that magnitude inside. So this is the same thing as the dot product of A with this vector here. But this is a magnitude and a direction. So this is, of course, just the vector B, right? Because here's its magnitude and here's its direction. So then this is the same thing as just B. So, and then if I multiply this side by the magnitude of B, you get the more familiar definition of the dot product. Some vector A dotted with some vector B is equal to their magnitudes multiplied by cosine of the theta, the angle between them. I'll point out that this angle is always something between 0 and 180 degrees. So when you have two vectors, like if I have two vectors like this, there's no ambiguity as to which vector or what angle to talk about, because there's technically this angle, which is the right angle to use, compared to this angle, which is greater than 180 degrees. And the cross product is referring to the one that is less than 180 degrees. Okay, so that just kind of reintroduces the more common more familiar definition of the dot product. This also gives the orthogonal test, the orthogonality test, or is it perpendicular? Because if the dot product is equal to 0, by this definition, or again by this definition, if the dot product is 0, these magnitudes are only 0 if the vector itself is 0, which is not very interesting. So given you have two non-zero vectors, these magnitudes are going to be non-zero. So the only way this entire thing can be 0 is if this is 0. And cosine is 0 when the angle is 90 degrees, or pi over 2 radians. All right. So again, geometrically, the dot product is talking about plucking out this this parallel component. That is really what's going on here with the dot product. But then when you write it like this, A dot B, where they're just regular vectors, of course, by symmetry, but the formula itself, right, makes sense that then B dot A gives you the same number, same answer. So then sometimes you'll see this written as A dot B is the magnitude of B multiplied by the component of A that's parallel to B. It's essentially taking this and plugging it in there. Or by symmetry, this is the same thing as the magnitude of A multiplied by the component of B parallel to A. Which again, I could redo this entire thing, but I could switch the letters and write B here and A here, and I would get the same exact sort of result. So, with this, we can actually then define a magnitude. I can define a way of actually computing the magnitude, right? I said the magnitude is the length of the vector, but I never said how to compute it before. So the magnitude, this length A, well, let me take the dot product of A with itself. Then by the formula, it's the magnitude multiplied by the magnitude. And then the angle between the vectors is 0, of course. Cosine of 0 is 1. So then it looks like the dot product is equal to the square of the magnitude, or that the magnitude is the square root of the dot product. You could use this actually as a definition of the magnitude, and computationally this is how you would this would be the efficient way of computing the magnitude. Say computational physics next semester. All right, so here's how you actually get the magnitude. Give me a vector, I'll take the dot product with itself, and that's my answer. But of course, if you think about it, based on what I've told you so far, we actually still don't know really how to do this, or it's circular reasoning, because right now all you know how to do is the dot product is the magnitudes multiplied by the cosine. And then I told you here's how you compute the magnitude in terms of a dot product. That's a circular argument, in a sense. I need another way to compute the dot product that would allow me to kind of tie all of this together. So let's just think about the magnitude. Let's think about the magnitude and then use the usual Cartesian axes. So I have some vector A, which then has some x component and some y component. And lo and behold, that looks like another right triangle. So I could think just by the Pythagorean theorem that the length of the vector, or the hypotenuse, is going to be the square root of this squared plus this squared. So in this case, by this drawing, the magnitude is just given by the Pythagorean theorem. So since the magnitude is the square root of the dot product, then this must be the case. Or if I square both sides, the dot product with itself, or A dotted with itself, then it looks like it's just going to be ax squared plus ay squared. I take the individual components and square them and add them together, which of course I'm getting just from the Pythagorean theorem. So then this kind of looks like what you are probably familiar with, where it seems like if I do A dot A, I take the x components and I multiply them together, and I add to them the y components after I multiply them together. And this, admittedly, I have to skip a couple steps here. You can then motivate that if I want to have a definition of the dot product with two different vectors, A dot B, then I essentially can just generalize this idea, where instead of it being the same component being multiplied by itself, A dot B is then AX BX plus AY BY, and then a B plus AZ BZ if it was a 3D vector. So typically, I imagine what is usually done is that you usually start with this definition and then you prove that it's the same thing as that. which is all well and good, and I know the reason why they do it, because the proof is much easier starting here and going this way compared to what I tried to sketch. And notice I skipped some steps along the way in terms of doing the proof. But I like thinking of the dot product as being defined as this projection, because then it ties me back into geometry. I'm always thinking geometrically, where this kind of feels like it's pulled out of nowhere. Like, why should that be the definition of a dot product? Well, you can get to this definition starting from this definition. Again, just takes some more steps. And this is not a math proof course. But I kind of hopefully have sketched kind of the basic idea. So you have two ways of defining the dot product. This is, the computational way. If you know the components, you can compute the dot product that way. And here's the geometric definition, where the dot product connects to magnitudes and the length and the angle between the two vectors. And the magnitude can then be defined as the square root of the dot product. All right, a couple quick examples of this. And suppose I have a vector that I say has length 3 and is 30 degrees counterclockwise from the y-axis. So this is kind of one way of defining a vector. I've told you a length, I've told you a direction. In this case, relative to these axes. And now I would like to know the components. There are kind of two ways to do this. The way I like, because again it keeps you thinking about what the hell you're doing, is that I look for triangles. So I know if that this is the length of the vector, looks like there's a nice little right triangle right here, where this kind of component here is the y component, and this component here is the x component. So if I have a triangle, and I know this angle is 30 degrees, or pi over 6 radians, then I just trig my way to the sides. Then the swoosh touches this side, so then this is 3 times cosine of 30 degrees, or 3 times root 3 over 2. And then this is the opposite side, so that's where the sine comes in. So this then is 3 sine 30 degrees. Sine of 30 degrees is a half. Those things I had to memorize in high school. I don't know if you have to memorize those things anymore. Sine of 30 degrees is a half. So in this case then, I know that this length is given by this, and this length is given by this. Now in order to make it a vector, since this is vertical, I will put this in the vertical location, and since this is the horizontal component, I'll put it in the horizontal location. But I have to remember to throw in that minus sign, because based on what I've drawn here, the arrow is pointing to the left, so negative x direction, and then it's pointing vertically up, so I expect a positive y component and a negative x component. Again, I like that because I'm thinking about what's going on and what I'm doing. The kind of blind way to do it, which of course, if you use this correctly, will give you the right answer, is just to think of this as the general formula, that the vector A is its magnitude times cosine of some angle, and then the y component is A times the sine of some angle. But then you have to remember, if you want to use this definition, that this angle is always measured counterclockwise from the positive x-axis. So in this case, it's not 30 degrees. It's 30 degrees plus 90 degrees, because you're always measuring from the positive y-axis in this case. So that's 120 degrees. And then you can just plug it into the formula, and you will, of course, then get the same answer as before. I say this with a little bit of hesitation, because I feel like people get into the habit of thinking about this formula and thinking x always is cosine and y always is sine. But then notice up here that was not the case. Right? In this case, when I did it, this way, the vertical component was we used a cosine because the swoosh touched that side, and then the horizontal component we used a sine, just because that's the way this triangle was drawn. SOHCAHTOA, that's just triangles. This, it's making the further assumption that you're always measuring from the positive x-axis. So don't think x is always cosine and y is always sine. This formula has it that way as long as you measure from the positive x-axis. Anyway. Here's two vectors, A, which has coordinates 1, 1, and B, which has coordinates 2, -1. These are not drawn to scale, I apologize. What is the angle between them? Of course, I can pick up this angle, this vector, and move it over, so I can put them both of their bases together at the origin. Then that allows me to define the angle I'm talking about. Because again, you can always pick up and move a vector. So then this angle theta here, the angle between them, how would I get that? Well, I know that the magnitude of A, which is the square root of its dot product, so then it's 1 squared, which is this squared, plus 1 squared, which is this squared. So that's square root of 2. Similarly, the length of B is going to be 2 squared plus -1 squared. I should have wrote -1, but then the square gets rid of the negative, of course. So that's square root of 5. And then the dot product, A dot B, is 1 times 2 plus 1 times -1. So then I have 2 minus 1, or 1. So then put it all together. The dot product, 1, is equal to the magnitudes multiplied by the cosine between them. Square root of 2 times square root of 5, same thing as square root of 10. Or that the cosine is 1 over the square root of 10. Quick little sanity check. 1 over the square root of 10 is less than 1, as it must be the case, right? Because cosine, the trig functions cannot be greater than 1, cannot be less than -1. So this is a positive number that's less than 1. That's a good sanity check. Then when I plug into my calculator, I get 71.57 degrees. Similarly, if I wanted to make a unit vector out of this vector, well, I already computed its magnitude, and it has a magnitude of root 2, which is not 1. So I can compute the unit vector version as doing 1 over the magnitude multiplied by the vector, which is then 1 over the square root of 2 multiplied by the original vector. In scalar multiplication, then I can just bring these in. So then this becomes 1 root 2, comma 1 root 2. This vector is a hat which has a length of 1. Notice it points in the same direction. These are parallel to one another. But these have different lengths. I could always do a self-check. It's always good to be able to check yourself. I can compute the length of this new vector. The magnitude of this new vector is the square root of its dot product. So it's going to be the square root of this squared plus this squared. 1 over the square root of 2, that's just going to be 1/2. And 1 over the square root of 2 squared again, that's just going to be 1/2. So I have a square root of 1/2 plus 1/2, square root of 1, which is 1. Indeed. It is a unit vector. I might as well do this. A little bit of physics to bring in here. That again, I've been going off on how vectors do not have to start at the origin, but then often I feel like so many examples have them actually start at the origin. But remember, here, it does not start at the origin. Here, I don't even have axes, drawn. It's a little confusing because I feel like we always say that, but then the first examples we always do are position vectors, which typically do start from the origin. So a position vector is telling you your location relative to some origin, some starting point. So just something to keep in mind. Position vectors typically do start at the origin, but vectors in general do not have to. So suppose I have some vector here, r. Maybe that's my position at some point t. Then I have some vector here, r, which is my position at t plus delta t. So at some later time. My displacement then is the vector that goes from this starting point to my endpoint. I'll call that delta r. Just by the rules of vector addition, there are two ways I can get to this point. I can either start at the origin and just go directly there, which is r of t plus delta t, or I can get to this final point by starting at the origin, going up here, and then moving over here. which that is just the vector r plus the vector delta r. So since I'm getting to the same endpoint at the end of the day, they must be equal to one another. So r at t plus delta t is the same thing as r at t plus delta r. Or delta r is their difference. Again, probably nothing too surprising here. But the thing I want to point out is, because we're going to need this for Coulomb's law when we do multidimensions, this delta r, which points from here to here, is something that comes up a lot, of just, if I need a vector that points from one location to another location, how do I know how to draw that vector? So, note here, this delta r points from r at t to r of t plus delta t. So it points to this location from this location. Yeah. And so this is something just to memorize. That when you have the vector a minus b, that is going to be a vector that points to a from b. Just how this here is pointing to this location from this location. To this location from the starting location. So a minus b points to a from b. It's kind of nice. You can think of it like a letter, a to from, letter. Kind of, to from then gives you to a from b. A student pointed that out last semester. I really like to think of thinking of it like that. So, given that, then we can define the derivatives of vectors, velocity, acceleration, which are defined in the usual way. Same way you define a scalar derivative, but you just have a vector. Again, to connect this to stuff we've done already, think of units. Think about what are the units of this thing. It's a position divided by a time. This is a velocity divided by a time. What are the units of that? So we can define this in the usual way. The derivative of position, which we call velocity, is the limit of these deltas as delta t gets really, really small. And then the velocity is defined as it's a vector that is tangent to the trajectory at that point in time. And similarly for acceleration, it would be tangent to the velocity vector at that point in time. Now I bring this up again because remember that a vector has both a length and a direction. So if I want to ask how vectors can change, which is all derivatives are telling me, how does r change? Then I'm going to think about the derivative. Well, I can change a vector by changing its magnitude, or I can change a vector by changing its direction. So, how do you change the magnitude of a vector? How do you change the direction of a vector? Well, let's take a very simple example. I don't know what these are. So, let me have some position r, and then I have some position at some later time, r at t plus delta t. And that, of course, then can be approximated by this formula here. Essentially, I'm taking the formula for the derivative and undoing it. So r at some later time is the original position plus v times delta t. Here I've drawn it here. So I have r, and then I have v times delta t. Again, why is it that versus just v? Well, think units. R plus v does not make sense. R plus v delta t has the right units. And I have r, v plus delta t, and then that gives me my final position here. Well, when I look at the original vector seems to have gotten longer. The magnitude has changed. It seems to have gone from this length to now something that's about this long. Also seems to have changed direction. It originally was pointing in this direction, but then it kind of has shifted and now is pointing slightly more down in that direction. And hopefully it's becoming clear where I'm going with this. If I have the original vector, how did I make it longer? Well, it seemed like that's a component parallel to the original vector. Then I have this vector here, and how did I move it over? Well, it seemed like what moved it over was the component perpendicular to that vector. And this is generally the case, that the parallel component to v, of v, right, really I should be saying parallel component of v, changes the magnitude of r. The perpendicular component of v changes the direction of r. And again, that's what we saw here. And you have the original vector, and it got longer. And essentially, this part here is the part of v that is parallel to r. That made it ultimately longer. Then I have the original vector that got shifted down a little bit. It got shifted in direction by the component of v that happened to be perpendicular to r. So this is generally, again, I love to think geometrically. I want to think geometrically. So when I have just a position vector, here's r. I have some velocity vector v. Just by this alone, I can say what's going to happen. I know that the magnitude is going to shrink. So it's going to go here, and then the component of v that is, in this case, anti-parallel to r is going to shrink the length of the vector. And then the part of v that is perpendicular is going to be then shifting the direction of my position. Now, of course, it doesn't have to be position and velocity. I could have v and acceleration. In this case, my velocity is going to decrease. So I can imagine it slowing down because this has a anti-parallel component. But then the direction is also going to shift towards the right because of the perpendicular component of the acceleration. All right. One last thing, and then we'll call it. Just something I noticed with the problem that we did for the lecture assessment. I'm not sure where this is coming from, so let's correct this issue now. So here was the problem again, that I have 3 charges, Q1, Q2, Q3, and then I said I put an electron at this location Q4, and I wanted you to draw or tell me the direction of the forces acting on Q4 from the other 3 charges. And Kittner said maybe that's because you didn't have a lot of examples with more than just 2 objects interacting for whatever reason. But in this case, all these objects are acting on Q4, so I expect 3 forces as a result. But when I asked for the forces on Q4, so the arrows I was expecting should have been drawn on Q4. I saw a lot of this, which is wrong in multiple ways. One, the arrows are pointing the wrong direction based on the question I asked. Again, if this is a positive charge and this is a negative charge, I expect them to attract one another. This is not the arrow that shows them attracting one another. Yes, Q1 is attracted towards Q4, but that's not what I asked. I asked for what is Q4 going to do. Q4 should be attracted towards Q1. So these vectors, and then similarly for Q2 and Q3. So these are not the vectors of the forces acting on Q4. Again, if it's acting on Q4, the arrow should be drawn on Q4. Now, you might be saying, what's wrong with these arrows? So this arrow is the force on Q1 from Q4. But again, that's not what I asked. This is the force on Q2 from Q4, on Q3 from Q4. But I wanted on Q4 from the rest of them. So that means the arrows should be drawn on the object I'm asking about. So on Q4, Q4 is pulled towards Q1. So this is the direction of the force on Q4 from Q1. This electron is pulled towards Q2. So this is the arrow on Q4 from Q2. Then it is repelled from Q3. So this is on Q4 from Q3. The arrow is drawn on the object Q4. Again, this arrow is on Q1 from Q4. Again, not what I asked. This is what I was looking for. Now, of course, all these arrows are related by Newton's third law, of course. That's why I like my massive subscripts. If this is on Q4 from Q1, this is on Q1 from Q4, just by the symmetry of the subscripts, right? Those are a Newton third law pair. On Q4 from Q3, on Q3 from Q4, those are Newton third law pairs. And similarly, these greens are Newton third law pairs. So, just point of clarification. When I ask for the forces on Q4, the arrows have to be drawn on Q4. I was lenient in grading if you drew this, because I think you were thinking correctly, but this is not forces on Q4. Something to keep in mind. All right, that was a whirlwind rush, but again, presumably we've seen all this before, and so hopefully this is a review. So think of if you could do kind of example problems, using these calculation techniques, or kind of what I meant here in terms of drawing forces, as a hint of what you might be asked tomorrow. All right.